still need one class to make up what I have lost. So we'll see that we will somehow get that through this itself. So we are back on track after. So we were looking at photoelectron spectroscopy, and if you see, we have looked at quite a few spectroscopic methods. We looked at rotations, and what information do you get from rotations? You get very accurate information about the structure, because you get good information on bond angles, bond lengths, and dihedral angles. In other words, you get information about structure when you get rotation spectroscopy. Yeah, we settle down. So, and it's probably true that the rotational spectroscopic method is probably the best way to get structural information. Right? We can't see any other technique beating it when it comes to getting structural information on individual molecules. X-ray crystallography will give it to you for a crystal, but then if you want a single molecule and you want to know the structure of the single molecule, there's nothing to beat rotational spectroscopy. So we saw that. Then we started looking at vibrational spectroscopy, and we saw that you could get information about bonding, essentially. You could get information about the nature of the functional groups. You get information about how strong the bond is, how weak the bond is, and so on. So that gives you information about the vibrational aspects, and therefore about the bonding aspects in molecules. This is a chapter going on, and that's bothering me. So then you get UV visible spectroscopy. And there what you're doing is essentially you're pushing molecules, pushing electrons from one molecular orbital to the other, and you're actually looking at changes in the electronic structure, and therefore changes in the molecular structure. We know that if you change the molecular, the electronic configuration for the molecule, then the molecule can actually change shape to accommodate for the new position of the electrons. So that's basically what UV visible spectroscopy does, and you can actually record the absorption spectra, the emission spectra, and get information about these orbitals. There is one other method which gives you rather good information about orbital energies, and that is the photoelectron spectroscopy, and which is what we were looking at. And what we said in photoelectron spectroscopy is we do is the following. You take the atom, let's say it's atom A, and then you knock off an electron, and you go to A plus, and the energy I need here is essentially the ionization potential. But if I now give energy that's this much, it's new, then the excess energy that I have given to the system, which is this much, will actually show up as kinetic energy of the electron. And if I can measure the kinetic energy of the electron, and I told you how to do it by essentially looking at the time of flight. Let's see how much time the electron takes to go from point A to point B. If you know the time and you know the distance, you know the velocity, you know the mass of the electron, therefore you know the kinetic energy. And once you know the kinetic energy, which is this part, you know how much this is, you will essentially get information where this state is actually lying. And therefore you get information about the energy of the ion state. And that is sometimes extremely useful. So you can get extremely precise ionization potentials of atoms and molecules by simply doing photoelectron spectroscopy. But you can push it a little bit more, and that's what we will do. If I take argon, what's the electronic configuration for argon? Right? You have helium, neon, argon, and that's where I am. If I now remove an electron from argon and go to argon plus, which is the electron that's the easiest to remove? Which is 3p. So essentially this fellow has a configuration positive 3s2 5. If it is this electronic configuration, what's the term state? I mean, now we are professionals, we have learned how to get term states. We should speak in terms of term states and not in terms of electronic configuration, because we know that for a given electronic configuration, we can have more than a few term states. Carbon, 1s2, 2s2, that's the electronic configuration. But what are the states coming out of that? Triplet P, singlet S, singlet D. And what's the ground state amongst them all? Triplet P. So you have triplet P, then you have a singlet D, and then a singlet S. So giving the electronic configuration is really no use, because I know I have all these states possible, and I can have transitions between these states. Whether they're allowed or not is another issue, but at least I know I can jump from one of these to another of these, where the configuration hasn't changed, and all that has changed is the relative orientation of the angular momentum vectors. So we have to speak in terms of term states. And what is the term state corresponding to this? Singlet S. Completely closed shell has to be singlet S. What happens over here? It's like P1. I'm not going to work for P5. It's like P1. And if it is P1, what is the state going to be? Okay, doublet P. But then I can have doublet P3 half and doublet P1 half. Which of these is more stable? 3 half is more stable. So that's wrong. When I remove an electron, I don't get one state. I really get 2 states. What's the lower state? Doublet P3 half. And what is this state? So even though I have removed one electron and I have produced one unique electronic configuration, that unique electronic configuration actually has 2 term states associated with that, simply because of the way these vectors can orient themselves. And you have WP3 half and WP1 half, and knowing fully well that the WP3 half has to be the lower in energy and WP1 half has to be higher in energy. We know that. So now when I take argon and I ionize them and I remove this electron, I can actually leave the argon either in WP3 half or I can leave it in WP1 half. So if I give an energy this much, I have 2 possibilities. I can leave the argon, goes into a 3p5, same electronic configuration, but it could be left in a WP3 half state or it could be left in a WP1 half state. If it is left in a WP3 half state, then its kinetic energy I am going to be getting out of it is this much. And if I leave it in a WP1 half state, then the kinetic energy I am going to get is this much. So if you actually do the experiment, the way I told you the last time around, how was that? You flash a beam of light and then start the process, then wait for the electrons to reach, take the time that it takes to go from point A to point B. What will you see? You will actually see 2 packets of electrons arriving. One first, a little while later, the second bunch will arrive. Who is the first one to arrive? The one with the higher kinetic energy. And who has the higher kinetic energy? This guy. A little later, the second bunch will arrive. And that second bunch will correspond to the one with the lower kinetic energy. And that should be one corresponding to WP. Yeah.
So what factors decide whether the electron will stop at 3 half or 1 half?
We'll get to that. Yeah, who decides whether the molecule or the atom will be left here or left here? That's your question. There are both possibilities. Well, both should be got. If I go for this for the energy, then I will get this and this. So your question really, you have to rephrase it. How much of it will go here and how much of it will go here? We'll see that. So now if I were to plot in terms of the kinetic energy of the electrons, what will I get? First I will get one peak with the lower kinetic energy, and then another one with another kinetic energy, higher kinetic energy. The higher kinetic energy will belong to what transition? Or where am I leaving the R0 to get this? And this must correspond to. And this energy difference, of course, it's in energy units. So what does that energy difference correspond to? This corresponds to this split in energy levels. And what is that called? The spin orbit split, or the spin orbit splitting for the given configuration. In other words, we kept talking about, and we said this millions of times over, right from the last 1 or 2 class, that if I have L and S, I can couple them and get J, and there are so many J's possible. But then we never really said what the energy spacings between those J's are. Of course, that can be calculated today rather easily. But more than that, the question is, how do I measure these energy differences? And I never told you that. But here's a neat method to measure it. All you have to do is to do a photoelectron experiment, and the energy difference between these two is exactly the energy difference between those 2 states. And therefore, Here is a technique that actually gives me the method by which I can measure spin-orbit splitting. Pretty straightforward. Do a photoelectron experiment and you get this. Now the question is, how much of it is left in 1/2? How much of the argon is left in 3/2? In other words, let me think of a hypothetical experiment. I gave you 100 argon atoms and say, ionize it. Of course, you have no control. You can't decide to go into one or the other. How does it partition? Okay, now go back to what you learned in rotational spectroscopy. I have a bunch of molecules whose rotations are constant, you know. I simply heat it or I keep it at a certain temperature. How do you decide who will go in J0, who will go in J1? It's the same question really. How do you decide how many will go into J0, how many will go into J1, how many will go into J2 and so on? What decides that? Yeah, I'm just heating it. Let's say I have a gas over here at some temperature, 300 Kelvin, room temperature. So, which J level will have the relevant population, or which J level will have the most population? Who decides that? What factor decides the population in the various J's? Temperature, I fix the temperature. Now what decides that? 2J plus 1. Right? It's the 2J plus 1 together with the energy, right? We have E power, we have the degeneracy as well as the energy. We said the energy, the higher you go, population has to come down. We know that. But then what's so different about rotation spectroscopy? The higher I go, the 2J plus 1 increases, isn't it? And therefore, initially the 2J plus 1 must be actually is trying to increase the population. Because for every J level, the number of allowed J or possible J levels is 2J plus 1. For J equal to 0, there is 1 J level. For J equals 1, there are 3. J equals 2, 5. For J equals 20, 2J plus 1, that's 41. So as I keep increasing the J, the number of levels I have to put my molecules in there actually increases. So that is going to help me increase the population in that particular J. But what is hurting me? What is hurting me is the energy. As I keep going to higher and higher J's, the energy increases, therefore the population must decrease. There are two things working against each other, and therefore what do you see? You see a most probable J. And what are the most probable J given by? If you remember the equation, root of KT by 2xCT minus 0.5. I don't expect you to remember it, but at least you know that what is really deciding the intensities in these, the degeneracy is playing a huge role. And as long as, of course, if the energy difference was this big, then of course there's no question of degeneracy. Because the energy difference is so big, then it doesn't matter how many states you have up there, the molecule isn't going to get there. But energy differences are small. Oh, the 2J plus 1 will play a huge role. And that is the reason why in rotational spectroscopy, where levels are separated by about 2 wave numbers, 3 wave numbers or thereabout, the 2J plus 1 relation or the 2J plus 1 parameter plays a huge role in deciding the population in these levels. And that is the reason why you have a most probable J or a most populated J. So the reason I'm trying to say all this is to drive home, recall the phenomena that 2J plus 1 is important. Now come back here. What is the J for this? Half. What's the J for this? 3 half. So what is the 2J plus 1 for this one? What's the 2J plus 1 for this one? And therefore you will find that there is a little difference as far as the 2J plus 1, the degeneracy is concerned. And that is, in this case it is 2J plus 1 is 4, in this case the 2J plus 1 is going to be 2. And therefore, what do you think will happen to the population? Who will have more population? Obviously this guy. Spacings are not very great, and therefore the one that has a higher degeneracy will actually scavenge along more population than the one with the lower degeneracy. So when I am doing this experiment, this fellow is likely to have a greater population because the 2J plus 1 corresponding to J equals 3 half is actually 4. And then 2J plus 1 or the degeneracy corresponding to J equals half is actually 2. And therefore, I'm likely to see a greater population here than a greater population over here. And in what ratio? Approximately 1:2. Because that's what it is. So when I do the experiment, actually, I won't get these intensities. I will actually get an intensity that will look like this. The intensities are actually reflecting the populations, and the populations are actually determined by the degeneracy of those states. And therefore, when I do the argon experiment, I basically will get two peaks in my photoelectron experiment. It should look like this. And the moment I see this, the ratio 1:2, I immediately know that the bigger one must be the WT 3/2, and the smaller one must be the WT 1/2. And I also know that the energy difference here must be the energy difference between the two spin orbit states, which is these two. And therefore, a photoelectron experiment actually gives me a huge amount of information as far as the spin orbit states are concerned and the eventual states that are produced by the configuration. When I do this experiment, let us say I have used H2, which is rather large. Let us say I need only like 5 eV to do this. But let's say I have used a photon that's of energy 10 eV. Enormous energy, much more than what I need. What can happen? I don't have to remove just this electron because that's the easiest one. But when I have given so much energy, what is possible? I probably can remove this also. If I remove this one instead of this one, then what is my electronic configuration up there? PS1, PP6. In other words, I have removed one of the inner orbitals. If I remove one of the inner orbitals, is it more energy demanding or less energy demanding?